We begin the next example by checking to see whether we have a proper or improper fraction. In this case, the degree of the denominator is 2, and the degree of the numerator is in fact higher, it's 3. So this is our first example of an improper fraction. Now, because this fraction is improper, that means we're going to have an extra step. Improper rational functions, we have to use long division to get an equivalent version of our rational function. This is where, again, if you've never done polynomial long division before, you should watch the tutorial video. For those of you that it's just been a while, this should be enough of a refresher. So I'm supposed to take x cubed and divide it by 1 plus x squared. So I'm just going to, when I rewrite my divisor, put the x squared in front. Now, the x cubed, you want to fill in the other terms of the polynomial. Standard form for a polynomial has the highest exponent term appearing first, and then we write them in order of descending exponents. Now, I don't have any x squareds or x to the first powers in this polynomial, but you're going to want to put placeholders in. So the only way to do that without changing the value of the polynomial is to put in coefficients of 0. So I have 0x squared, I have 0 x's, and I have no constant term. Once you've established any missing terms of your polynomial, you're ready to begin the division process. You're going to compare the first term of the polynomial to its divisor. And you're going to say to yourself, what would I need up here so that when I multiply by x squared, it becomes x cubed? Of course, that's going to be x. I need to remember to use distributive property when I now take this x times the divisor. X times x squared is x cubed. X times 1 is 1x. However, I don't want to put this plus x in this position because I want to maintain columns for like terms. So instead, I'm going to move the plus 1x here. Now at this point, you need to remember in the long division process, you are subtracting the two rows. So x cubed take away x cubed disappears, which is what you want to have happen. 0x squared take away nothing is, of course, just a 0x squared. 0x subtract 1x would actually give us a negative x. And again, I can bring down the plus 0. Now, at this point, I don't want to bother paying attention to a leading coefficient of 0. I could go back up and say, okay, what times x squared gives me 0x squared, but I'm just going to end up putting a plus 0 here, which has no value. So if you have a leading coefficient, the coefficient in front is 0, you can ignore that term. And now when you compare the highest exponent term to your divisor, if that highest exponent, which here's a 1, is less than the highest exponent on your divisor, you are done with the long division process. So again, I don't need that 0 at the end. So I'm just going to clean this up. All that's left as a result of my division is this minus x. That's what we call the remainder. And the proper way to write a remainder is to go back up to your quotient. You have x. I'm going to put a minus sign down because my remainder is negative. I'm going to put my remainder, and you always make it a fraction over your divisor. So what I've just accomplished is I've taken my original improper fraction and I've written it in terms of a polynomial, which my polynomial here is just x, and a rational function. This is now a proper rational function. So I'm going to begin by rewriting my original integral as an integral of those two pieces. Now, at this point, We would normally talk about this improper fraction, and we would talk about, okay, we need to do a partial fraction form for it. So I would go ahead and say, okay, I'm going to take the fraction x over x squared plus 1. I'm going to write it as a sum of other fractions. But pay attention to the fact that you only have a single factor in your denominator. So normally we take our separate factors and make a fraction with each one. Because we only have one, we should stop in our tracks and think. So at this stage, going to a partial fraction decomposition doesn't really make sense. So what can we do instead? Well, next up with fractions, I would usually try u substitution. So I'm going to go ahead and let u be my denominator. My du then becomes 2x dx. And I can move that coefficient to the other side. Now at this point, I'm actually feeling like I'm on the right track because when I compare my u to my original, I can see where they match. And then the x dx also shows up in the original integral. So therefore, u substitution is going to take care of this one just fine. So we don't, in fact, need to do a partial fraction decomposition here. I'm going to go ahead and just carry down the first integral. When you integrate x, it becomes x squared over 2. I'm going to write the equivalent u integral for the second integral. So that's going to become, the u is on the bottom part of a fraction. We have the x dx becomes a half du. So I'm going to put the half in front, the du at the end, and because there's no numerator, I'll just fill in a 1. As we've seen before, this is simple to finish integrating. And please note at this point, when I put my u back in, because u takes x, squares it, and adds 1, that will always be positive. So I don't need the absolute value bars here. It's not wrong if you put them though. And there's my answer. In the next example, we begin by comparing degree of numerator and denominator to see what kind of fraction we have. This is an improper fraction because the degrees are equal. And anytime you have an improper fraction, you need to take care of that by performing long division. So I'm going to take x squared plus 8 and divide it by x squared minus 5x plus 6. Now, before I begin the division, I need to fix my polynomial underneath the division sign because it has an x squared term. It is missing the x term, and I want to have a column for that, then put on my constant. This way things will stay lined up when I perform the division. I begin by looking at the first terms and I say to myself, what would I have to multiply x squared by to keep it x squared? Well, that's just 1. So now I'm going to use distributive property and multiply each term of my divisor by 1, giving me x squared minus 5x plus 6. Now when I work down each column here, please remember again that we are subtracting. So x squared take away x squared is gone. 0 take away a minus 5x is the same as 0 plus 5x, which is 5x. And 8 subtract 6 is 2. My degree of where I'm at in my division is now less than my divisor, so this is in fact my remainder, and I will stop the division process. This is a positive 5x plus 2, so I'll hook this on with a plus sign. I take my remainder and put it over my divisor. And you can see I now have a polynomial, which is the 1, plus a proper fraction. So I'll begin by rewriting my integral in terms of those two pieces. Here's my polynomial integral. Here is my proper fraction. Now I need to look at what I have in my denominator here, and I have a quadratic. I need to figure out if it's reducible or not, so I know how to set up the partial fraction form. This one, is there a pair of numbers that would multiply to give me 6, and the same two numbers would add up to -5? The answer is yes. So this is a reducible quadratic. I will go ahead and reduce it, meaning write it in terms of linear factors. And those linear factors will be x minus 2 and x minus 3. So when we consult our table of partial fraction forms, we don't have a quadratic irreducible. We had a quadratic that was reducible. We were able to write it as linear factors, and they don't repeat. So we're looking at the first case. So I'm going to perform the partial fraction decomposition for 5x plus 2 over x minus 2 times x minus 3, which the general form is going to be split up those linear factors into two separate fractions, and the numerator will be constants. So I'll put an a here and a b there. Now you work on the right as if you were going to add these two fractions together by getting a common denominator. X minus 2 is missing a factor of x minus 3. So I will multiply my numerator and denominator by that missing factor. The second fraction is missing an x minus 2. So I will again multiply numerator and denominator by that missing factor. I'm going to go ahead and distribute at the same time as I create my numerator. So I'm going to do a times x and a times minus 3. So I get ax minus 3a plus bx minus 2b all over my common denominator of x minus 2 times x minus 3. Now I want to group my like terms. In my numerator, my x's are ax and bx, so I factor out the x. I have a plus b x. And then I want to group my constant terms. I have a negative 3a and a negative 2b. So all I've done is gather the x terms together and the constants together so that I can now compare that to what my numerator on the left side is. So my coefficient on x on the left is a 5. On the right, that coefficient is a plus b. So I'm going to set those equal to each other. Coefficient of 5 equals a plus b. Then I'm going to compare my constant terms. I have a plus 2 on the left, and I have minus 3a minus 2b on the right. So I have 2 equals negative 3a minus 2b. This is now a system of two equations with two unknowns. As we saw before, I could go to the simpler looking one, solve for a variable and substitute. But there is a second technique, and it's called elimination. What I would want to notice is I have a minus 2b in this second equation. If I had a plus 2b in the first equation, I could combine the equations and the b's would eliminate each other. I can do that by multiplying this whole first equation by 2. So 2 times 5 is 10, 2 times a is 2a, 2 times b is 2b. When I line up the other equation directly underneath and then combine the equations, I get 10 plus 2 is 12, 2a take away 3a is negative a, and the b's are eliminated. I would finish getting a by itself by dividing off that negative 1, and I learned that a should be negative 12. Now I can go back to either equation. I like the nice easy one I started with, the 5 equals a plus b, substitute the a value, and I can find out what b must be equal to. Now that I have a and b, I can write my partial fraction decomposition. And I can substitute in those constants. Now I just integrate each of these pieces. For each of these fractions, you would go ahead and do a u substitution. I'm going to just skip to the end. And done. All right, I'm going to throw one more example in here. So in this example, we have a factored denominator. I still need to begin by determining my degree of my numerator and degree of my denominator. So to do that, I would FOIL out my denominator. And when you do that, you get what you see here. So this is in fact a proper fraction where my degree of my numerator is less than my denominator. So I'm going to go ahead and try and find a partial fraction decomposition. I'll go back to looking at the factored form and take a look at what kind of factors I have. This first factor is an x to the first power, so that's a linear factor. And then the next one, x squared plus 4, is quadratic. And I need to figure out if this is factorable. And it turns out it would be factorable if it was subtraction, if it was difference of two perfect squares. But this is in fact not factorable. There's no greatest common factor. It's not a trinomial. There's no difference of two perfect squares. So this is the first time that we see a quadratic that is irreducible. I'm not going to be able to change it into a product of linear factors. In terms of what that means when you're looking at this table, I have two different things going on in my denominator. I do have a linear factor, and I have a quadratic irreducible factor. And you can kind of go ahead and combine these two things together to create a unique partial fraction form. What you're going to do is set up any linear factors like you see in the beginning here, and set up your quadratic irreducibles this way. So essentially what it comes down to is your linear factors will always have a numerator that should just be a constant, and your quadratic should always have a numerator that's a linear expression, an x to the first power plus some sort of constant. Going back to my example, I'll start the partial fraction form. So on the right, I'm going to take my first factor and make that the denominator of a fraction. And because this is a linear factor, I will put an unknown that's just a constant. Plus, now I take the other factor that appears in my denominator, which is an irreducible quadratic, and that requires a linear expression in the numerator. So I will have a bx plus c. So you can see now I've got three unknown values, which is going to require me to write a system of three equations. To get to that point, you continue as usual. So you try to combine the fractions on the right by getting the common denominator. I'm going to use the distributive property on this first numerator. So a times x squared is ax squared plus a times 4 is 4a. Now, because I've got my first linear factor in my numerator, I've created two binomials. So I'm going to need to use FOIL double distribution to multiply these two out. I've finished the multiplication, and now I want to group like terms together. So I have an ax squared plus a bx squared. So I'll take those coefficients of a and b together on the x squared. I have two x terms. I have a negative b plus c on an x. So I'm going to be careful with my signs here. Negative b plus c on an x. And my constant term has two parts to it. I have a 4a take away c. So plus a 4a take away c. So in front of the x squared is a 3, and on the right that's a plus b. So that's my first equation. A plus b will have to equal 3. My coefficient on my x is negative b plus c. My coefficient of my x on the left is 1. So I'll have negative b plus c has to be 1. And my constant of 4a minus c has to equal the constant on the left, which is 11. Now this is 3 equations, which is good because we have 3 unknowns. So what you basically need to do now is start to eliminate variables one at a time. I see an easy way to do that when I look at these first 2 equations. I have a negative b, which would cancel out this positive b. So I'm going to take and write this second equation below the first, kind of reorganizing things a little bit. I'm going to line up the b's. I have a plus c, which I'll just create a new column out in front. And I have an equals 1. So now when I combine these equations together, I have 1c. This is a positive a, so plus a equals 4. I've eliminated the b's. Now compare that to the third equation, which is also in terms of a and c, and I can see a simple way to eliminate c. If I line up this equation underneath, the a's together, the c's together, and the constant, I can combine these equations to eliminate c. And I find out that 5a is 15, therefore a has to be 3. Now I can just go back to my previous equation. C plus a has to be 4. So c plus 3 has to be 4, meaning c has to be 1. And now the only value that I don't have is my b. So I just find an equation that has b in it, like this middle one. I have negative b plus c has to equal 1. C is 1, so I have negative b plus 1 has to equal 1. Therefore, b is going to have to be 0. So I've just found the values of all of the constants. I can now write my integral in its partial fraction form. I'll go ahead and fill in the values for a, b, and c. And now I'll clean things up a bit. I'll take my constant out in front to prep this first integral for integration. And in the second integral, 0 times x is just 0. So I'm really just integrating the fraction 1 over x squared plus 4. Working with the first integral is a simple case of u substitution. However, if I try to do the same thing on the other side, I get dw equals 2x dx. And that makes me a little bit nervous because I've got this x here then, and that doesn't match any part of my original integral, which makes me think, okay, maybe I need to go back to the drawing board. What is beneficial with that integral, this one again is just going to be very straightforward. With this integral, what we actually want to do is factor the 4 out of the bottom. Now, at first, that looks a little bit uglier, because if you factor 4 out of x squared, it becomes x squared over 4, and then plus 1. You can see how if I distribute the 4, I'd get the original back again. But what would be the reason that I would do that? That allows me to take the constant out, so I now am able to pull out the 1/4. I have the integral of 1 over x squared over 4 plus 1. So this first integral is going to be natural log of u, which is just the natural log of x plus 1. The second part here, I'm going to do one more rewrite, and I'm going to write this as x over 2 squared plus 1 in the denominator. Now again, hopefully you can see that if I square both parts, I do get the original back again. The reason I want to do that is now this has the format of a numerator of 1 with something squared plus 1 in my denominator. And that takes us all the way back to here. The only difference between this and where I'm at in my problem is instead of just an x, I have an x over 2. But that can be taken care of using a u substitution. Remember, x over 2 is just the same as 1/2 x. So if I take the derivative, I get 1/2 dx. I can move the constant over to the other side and I get 2 du equals my dx. My first integral, again, was simple enough to evaluate. It's going to be natural log of u, and u in that case was x plus 1, plus 1/4 the integral of 1 over u squared plus 1. Now dx equals 2 du, so I have to put a du here, and I need to get another 2 out in front. 1/4 times 2 is 1/2. And now this integral is the inverse tangent of u. I finish by substituting my original u back again, and I've reached the finish line. I'm not expecting at this point that you would necessarily look at this thing that we started with back here and think of the inverse tangent, but it's a situation where the more times we introduce this idea, the more comfortable you'll be in recognizing it when it shows up. So we've covered a whole lot of examples, so time to practice, my friends.